finding an exponential model for your data. So to begin with the linear model, or contrary to the linear model, exponential model has a variable rate of change, or the rate of change varies as you go, so we don't have a slope to find. What we have is essentially the percent change. Now you can see the formula up here gets a little complicated in that we're taking the quotient here and raising it to fractional exponent power. So it gets a little wordy, and once you get that done, take the average to get our starting value, just like we did before. Again, that's going to be the starting value for our base, and then we can find a starting initial value in order to come up with our basic exponential model, which we've seen up here before. Now, our exponential model that we've found thus far, using this initial value and this base, we can see fits fairly well. We've got 74 to 73, 73, 72, and so on. So that's a fairly decent model. We can get a better idea for how well this models our data by going ahead and plotting it with our data. Here's our exponential model. The x values are going to be the original x values. Y values are those of our exponential model. Hit the go button, and we get this. Now, first off, this looks a little linear because our base is 1.00002. Our base is so close to 1, it is going to look very, very linear. Okay? The other thing you notice is that we're increasing as we go from left to right. The values seem to increase, whereas our data looks like we should have this kind of an exponential curve to it. Okay? So that's what we want. We want some kind of curve to model that data. In order to obtain that kind of a curve, we're going to have to change our b value. Most notably, we'll change our b value to be something between 0 and 1. That will help to get at least the right increasing, decreasing nature. That'll make our curve decreasing like we want. Same concavity, but it'll get us decreasing. But that's going to require quite a bit of guess and check with that value for the base. And of course, every time we change your base, we're also going to have to change our initial value. So that's quite a bit of work. Perhaps an easier way is to use the log of y. So you can see here, I've got log of y. I just use log base 10 for simplicity. And then log of y plotted with our original. So this graph is our log y's plotted with the original x values. Those are the blue dots. And then it came up with a linear model in the same way we did with the previous video, basing these two values, at least initially, on our trend line that Excel can give us. So we've got a nice linear model that seems to at least be decreasing as it goes through those points. And now I can use some transformations to change my slope, my m and my y-intercept b, into a and b and our exponential model. So let me go ahead and get rid of some rows here to make this a little more clear. Then I'll go ahead and zoom out so that we can see both curves. First off, I want to go ahead and let my a value equal 10, because down here I took log base 10, so I'm going to let my a value be 10 raised to the y-intercept power. Okay. Notice all these will now change. And my base, I'm going to let that equal 10 raised to my slope power. Hit go. And we can see that things change. Here I've got my slope, or my base, between between 0 and 1, and my initial value went ahead and changed. But what I want to reflect most on, if we don't feel that this is a good fit for the data, we can change it slightly by changing, for example, this b value down here. Now if I enter in a different b value, say simply 1.8, Notice we've got a change here on this lower curve and on the upper curve. Okay, by doing this, now with this data we don't see much of a change, but by doing this and seeing both curves, we can real time see how M and B are affected, or how they affect A and B up here, our initial value and our base. Okay, so if I keep messing with this, bring it back to where it was, 1.879 I believe, that'll get our line right in the middle of our data. Remember, this is B value is just adjusting the height of the data, the height of the line, and that's also going to affect our base up here for the exponent. So as an exponential curve, this is going to be the best that we can hope for our data, okay? Because it still doesn't have quite that quite that curviness that we want. Chances are it's going to be another function that better represents our data. But this is the process we can use to come up with the exponential model for our data. And of course, oops, still inking. And of course, if we wanted to go ahead and write out our exponential model, we would write it as y equals, y equals roughly 75.68 times 0.99999 raised to the x power. Okay. Now again, being close to 1, this means that it is going to look very much linear. We can change that, but that'll also require some changes with our exponential curve. So the most simple exponential model we can come up with is this. If that doesn't fit well, we can either go with a different type of model, or we can use transformations